Um, so thank you, Gerard, for a very generous introduction. I'm really not sure if I can do justice either to that or to this poster that I received last week, and I was just shocked, and sent it to my kids, and my daughter thought it looked like a rock concert. And I'm a poor musician, so I don't know how much of a how good a job I can do to justify that. So I'll try to give you like an overview of some of the work I've done, and hopefully we'll have some time for questions at the end. So I'll try to keep it at a at a higher level. A lot of the work I do is mathematical, but there won't be a single equation in this lecture. So I hope that's a good thing. So what I want to do is kind of initially kind of just define a few things, few terms, very few simple terms that we use, and talk about applications to three areas and conclude. Okay, so that's my overview. The first definition of a dynamic system, because that's in the title. What's a dynamic system? Again, these are words in English, but they're more precisely defined in the context of this lecture. But basically, it means characterized by variables that change with time. So when you think about this, that really characterizes a lot of things. In fact, there's almost nothing in the world stays static. So really, it's everything, right? Obviously, I'm not proposing to have done research in everything. So I'll specify a narrower path here. If you look at the original dynamic systems, it really came from Isaac Newton, okay, about 400 years ago. So Newton's Newtonian dynamics is what it's now called, to distinguish from other dynamics. And of course, later on, then there was electrical systems, for example, and which are, again, you applying dynamics to it. There were fluid systems, again, came out of Newtonian dynamics. So there are a lot of engineering and scientific systems that qualify under that, of course, including astronomy. Then later on in the early 20th century, talking about quantum mechanics and so on, right? So it's really, they're all really dynamic systems. A big application of dynamic systems is meteorology, and I'll talk about some of the aspects of that. And then, of course, in the I guess after the stock market crash in the 1930s, they started to look at it and saying, well, can we somehow analyze this and figure out what's going on? And that's kind of really what give rise to a lot of economic system modeling, which borrow a lot of this same concepts from dynamic systems that we'll talk about today. And then later on, in the last maybe 20 years or so, there's been a lot of attempt to look at ecological systems and all kinds of biological systems as dynamic systems and apply the same principles. There's no end to it. One of the books I picked up recently, about 10 years ago, no, less than that, maybe 4 or 5 years ago, is called The Dynamics of Marriage. And it looks like a general thing, but actually it's full of equations coming from Newtonian dynamics modeling marriage. And my wife got a kick out of that, but because it talks about when it fails, for example. So obviously, that's an important consideration. So that's sociological dynamics. Given that it can be very generic, and again, I don't claim to be an expert on all this. I'm just curious about all these areas. So I'm going to define a few words that we will use. The first word is modeling or model. So if you look at any of these systems I talked about, they're very complex, right? And one of the first things we do in engineering or science is define something that's simpler that we can analyze, right? And that would be a model. So it's an approximate representation of reality. Right? The reality is something very complex, and we come up with something simplistic. And in the process of doing this, we make a lot of assumptions and approximations. Right? You have to make them simple. And typically, we use a lot of empirical principles. So if you go back and look at Newton, for example, Newton's was the famous laws F equal to ma, or Einstein's was E equal to mc squared, general relativity, and so on. So these are some kind of a mathematical model that we observed to be true from experiment, especially Newtonian dynamics. And then we say, we're going to apply that, right? So there is something that comes from empiricism, from observation, right? Okay, that underlies in the model. The second thing we'll talk about that I'll we'll touch upon is what's called analysis. So analysis can be very generic, but in this context of dynamic system theory, it basically means predicting behavior. So I have this reality, and I would like to kind of do something with my model, essentially a thought process, and that will result in some prediction that I now want to apply to reality and say, is this what reality, that I am going to observe in reality, right. So, that is called analysis. And in quantum dynamic systems, a lot of people do control, including some of my colleagues here, which is usually an addition of another dynamic system in order to accomplish an objective. So, if you talk about control, a typical simple control system we all use is a cruise control system in your car when you set your speed, which basically does some kind of a measurement to see what your speed is and adjusts it to try to keep the speed to be constant, right. So, that is adding another dynamic system, modifying it in some fashion in order to accomplish some objective, in this case to hold a constant speed. Optimization is another the concept that comes up in this context, and that is designing a system in order to achieve best performance. I think everybody understands what optimization is, right, to get the best performance, however you define best. And finally, an area that I have been doing a lot of work on and I will focus on in this talk is diagnostics. And diagnostics is usually finding something is wrong, right. So, you go to a doctor and they look at you and say, well, everything is okay, but it may be a good idea to get an EKG, right. So, there is a diagnostics that happens. Let us make sure your heart is okay. So, that is really, if you want to really define what diagnostics is, it's determining a departure from the ideal. Here is an ideal system, again quote unquote, and there is a lot of fuzziness with this, right. But let us say if we can define an ideal, how far apart are you from this ideal, right. So, that is diagnostics. Okay. So, I am going to use these words such as model, analysis, control, and especially diagnostics as we go along. So, modeling is something that I have spent a lot of time on. So, I would like to focus a little bit more on modeling, and finally and ultimately modeling is not just the technique, but it is also the art of representing a real complex system in a virtual world. A virtual world could be just a set of ideas, could be a set of mathematical equations, could be a set of graphs, whatever, right. So, it's we are kind of mapping out something really complex in a virtual world. So, there are some trade-offs with modeling, and this is fairly obvious, right. The more complex the model, the more realistic it is, because reality is in general complex, but the simpler the model, the easier it is to deal with. So, it is always a tussle between these two. So, what do I do? Do I take a simple model? If I take a simple model, it is easy to deal with, but I am not able to represent reality well enough. So, I am going to be off in my predictions. Okay. But if I want it to be more realistic, I need it to be more complex, right. So, no less than Einstein said basically you want as simple a model as possible that still explains everything that you want to explain, right. But the idea is always pushed towards as simple a model as possible, not a complex model, right. So, that is an important concept in pretty much all of physics and engineering. And one important point I want to say about empirical laws, because a lot of things we talked about like economic systems. Well, what is a law in an economic system? Or what is a law if you're applying something like this to a cognitive system, for example? Where is a law? And really, a lot of them are we really don't know. There are models that describe how, for example, a predator prey, right. So, you have rabbits and foxes. How does a fox population oscillate with respect to rabbits, for example? That is a pretty standard dynamic system model. Well, where is a law in that? We really do not have a law, right. We kind of just come up with some fairly arbitrary things and then observe it and say, this kind of works, so we will use it. So, there is this problem with how good the law, how good a law is that you have. Okay. In economic systems, that is in fact often a source of conflict between people. Well, this is not good, this is not good, depending on which spectrum of the politics you come from, right. That is a typical thing that actually happens. Should money trickle down or should it go up? That is actually a part, underlies a certain assumption in the law of economics. Okay. Then the kinds of models, models can be, there are a lot of issues with this. For example, how big a model do you want? Do you want it to be a deterministic model or a stochastic model? Do you know everything that is going on and can you write this, or do you need to say, well, I kind of really do not know, but I have a rough idea what the average values are, for example. Okay. Okay. So, the last one I skipped over here is linear versus nonlinear. So, what is the concept of linear versus nonlinear? I do not want to get into the mathematics of this, but let me just talk about the fact that nonlinear models are the more complex models, and it turns out that all reality is nonlinear. Okay. So, if you think about linear versus nonlinear, a simple example might be something that is not linear would be if you look at the fluctuation of temperature over a day, right. So, it kind of it's what 45 degrees right now and it drops to 30, and tomorrow hopefully it comes back to 45 and then goes back to 30. So, it oscillates. So, it is not linear, it oscillates, right. So, most phenomena are the laws underlying most phenomena tend to be nonlinear, they are not linear. So, why is that a problem? Well, it is a problem because they are qualitatively different, not just an accuracy issue. It turns out that nonlinear things, nonlinear phenomena that you observe are very different qualitatively. Okay. So, as an example is what are called instabilities. Okay. Instability is an example of where things are relatively well, good example of instability is probably snow. Snow is an instability, right, in the sense that it's getting colder and colder and colder, there is some mass, and maybe you get water, meaning rain, or maybe you will get something solid form such as snow. That is an instability. Does it fall on this side or does it fall on that side? Okay. There are a lot of engineering system instabilities that you observe, and usually it is a bad thing. Most of the time it is a bad thing. When you get a instability in an aircraft, that usually means it is going to crash, for example. Okay. So, and this only happens in nonlinear systems. So, that is something we observe, and if you want to predict it, we got to use a nonlinear model. There is in fact a word called strange attractors. The word is called strange, it is a technical word. The very fact that it is strange tells you there is something strange about it. Attractor is very simple, right. Attractor is something that attracts, that makes a system, dynamic system, settle into some value. Okay. So, for example, the temperature settles into some value. What strange attractors are a class of what is called chaos. Okay. And you probably heard about what is called chaos theory, the butterfly effect, which says if there is a butterfly flaps its wings, what is the effect that you see? Well, it could be completely different, right. So, there is this concept of tiny little changes somewhere that leads to huge changes somewhere else, right, and that is called chaos theory. Chaos theory is why, for example, if I knew everything about let us say all the properties when I toss a coin, I knew everything about it, my fingers and what I do and so on. If I could model everything, I still would not be able to predict if I get head or tails. Okay. So, there is an unpredictability about a lot of dynamic phenomena, even if I knew everything about it, right. And that is a consequence of chaos, and this is again nonlinear effect. Okay. So, chaos theory is a very interesting phenomenon that was only discovered, well, it was discovered about 100 years ago, but it was really kind of, people have been digging into it only for the last 30 years. Weather is an excellent example of a nonlinear system, and you keep thinking, oh, we are going to be able to predict exactly what happens. Actually, it turns out we will never be able to predict exactly what happens, and that has been proven, right. So, that is what is fascinating about this. It is not a question of, oh, we are going to get better and better and better with years and with supercomputers, not really. Okay. And that is the concept of nonlinearity. Stock market excellent example. If any of you have money in your retirement account, you know what I am talking about. In terms of failure of all kinds, anytime anything fails, it is a nonlinear system. Okay. It is a nonlinear phenomenon, and so you need nonlinearities to predict all of these things. That is my point, which means your model has to have at least that level of complexity to do this. All right. So, this has been my source of interest. All right. Okay. So, I am going to just talk about very briefly about this. So far we have talked about what are called physics based models. So, but I have also delved into another kind of modeling. So, I am going to just describe this and then get into some applications. Okay. So, physics based models uses physics, again it could be, I say physics in quote because this could be chemistry, this could be biology, this could be whatever, all right, whatever kind of law that you have or principle that you have observed, you use that to come up with a prediction, right, with a predictive model. So, that is physics, usually nonlinear like I just said, and the advantages of using a physics based model, it kind of captures the effect generally, but it is very difficult to predict exactly what goes on, right. So, for example, if there was so let us talk about something like my human body, which may be better appreciated by most of you, right. So, if I wanted to predict exactly when I am going to have a heart attack, God forbid, right? Okay. And if I had, all measurements done, so they cut me open, they measure every artery, every little particle in my body, and they got all this model, right? And then they build a physics, chemistry, it's all physics and chemistry, right? So they build all these models into it, and they write this big computer program, and they say, all right, now we can tell what your blood is going to do tomorrow, and we can put, what food you put in your mouth, the whole business, right? We can kind of start modeling you. Well, it turns out that even in that case, it be actually, and there are models like that, right? Actually be very difficult to say exactly if I am going to have a heart attack. But what they can do is that people of maybe my general habits and people with my general constitution, for example, they will be able to say generically what would happen with me. Okay, not specifically what would happen with you, but generically people like me. So they can say, well, if you put on 10 pounds, maybe you will have more likely hood of having a heart attack, whatever. Okay, so they can kind of predict this generality, and that's what's true about physics based systems. Whether it's machinery you're talking about, with a robotic system, you can kind of generically explain what happens, not specifically. Okay, it's very difficult to do that. But on the other hand, there are a lot of insights. We love these kind of models because they give us insight, really kind of understand what's going on, what kind of phenomena happens, right? So a lot of the advances that have happened over the last 400 years or so, has really happened because of the development of this. Okay, so let me skip this. So let me just make that one point. So nonlinear dynamics makes behavior unknown and unknowable, right? Pretty much. Okay. The second thing that I have kind of delved into for the last about 10 years is actually looking at what I decided to call database models. So database models is where you kind of have data and you establish a pattern. So for example, that's how, for example, human beings learn. If I'm learning to play a game, I don't sit down and write a physics model for it. I know that if I hit it this way, the ball is going to go this way, right? Why? Because I do it 100 times, and I observe it, and from the observation, I draw a pattern, a model for how my system is going to behave. I know what my strength is, right? All of this is going to be built into this, not using a physics-based model that looks at the forces and all these other kinds of stuff, right? So a lot of the learning human beings probably happens using some kind of a pattern recognition system. Okay, walking, baby learns to walk like this, right? Even language, for example. I don't want to say anything that's wrong with some experts in psychology sitting here, right? So, but but there is a data-based pattern that you could apply for any kind of system as well, right? So it's often called computational intelligence, sometimes called machine learning. There are all these kinds of techniques, sometimes called artificial intelligence, right? So the advantage of this is that it captures specific information for individual systems, right? So for example, I know if I look at myself in, let's say, playing a game, I know how I behave. So it's very specific. I cannot really apply it to somebody else that easily, right? So very, very specific, because unless I collect data about that person, right? So it's very difficult to generalize, and it gets better and better with more data. That's why the more a baby tries to walk, the better the baby is going to walk. Simple, right? The more a baby listens to other people speak, the more she or she can speak, right? So the limitations are is data dependent, cannot be easily generalized, right? And finally, it's somewhat of a dumb approach because it ignores science. Whenever you have science, it kind of ignores it, even then, right? So my focus has been, how do we kind of take this physics-based model and database model? They have their own advantages. How do we kind of combine them for all these things we want to do? That's been one of my focus areas. Okay, so let me talk about some examples. Okay, so I'm going to talk about 3 examples: machinery, robotics, and biomedical diagnostics. They're kind of different, but I'm going to give you a very high level overview of this. So a lot of the work that I started to do was on rotating machinery. So looking at which are primarily rotating shafts. Okay, so a simplest rotating shaft is a dentist drill. Okay, a dentist drill is an excellent rotating because it's a pretty high speed, right? I think it's like 10,000 RPM or so. And I'm always looking at this, and not always. I've had my own encounters with the dentist a few times, but I'm always afraid because I think about what's the vibration at this end and what's the level of inaccuracy that you're going to get because it whirls around. There's some inaccuracy. But that's a very interesting problem. It's supported at one end, usually on bearings, and of course any kind of drill that you use, right? A motor shaft. Or things like this, which is an aircraft engine made by Pratt & Whitney, and you can see this, that is the shaft, right, and then there is stuff on it, right, and then these are supported on some kind of bearings. Okay. So, that is a typical thing, typical rotating machinery. This speed, the speed of this is around 300,000 rotations per minute, right. So, that is it is not unusual for systems to have small, especially small systems, to have as much as 500,000 RPM or more rotations per minute, right. So, these are very high speed spinning shafts, so they bring with them their own problems. This is a steam turbine. This is pretty big, made by Siemens, and these tend to be like you will go to Pico, you will see that, right. So, these tend to be heavy and slower, so maybe like 100,000 RPM rotations per minute or lower, right. So, these are even the slower ones are pretty fast, right. So, these are pretty high speed systems, and they bring with them a lot of issues. They are also sort of what I call multidisciplinary systems, because they are supported on things like bearings with their own physics. They are supported on electromagnetic bearings, which bring electrical systems into it, fluid film bearings, which bring fluid mechanics into it. So, so you need need understanding from all of these to analyze this, all right. So, I have looked at the dynamics of this, and the typical problems that you get with this is that first is vibration. You got a lot of vibration, right. So, you do not want vibration, and you want to be able to reduce the vibration down to some level. Okay. So, I will come to that picture in a second. Bearing failures are quite common. If there is a bearing failure, usually the system will seize. So, if a turbine in the Pico nuclear plant seized up with a bearing failure, we would all know about it, because there will be a big problem. You can have fires, you can have all kinds of things, right. So, it is not a trivial thing. So, they want to prevent the bearing failure before it happens. Okay. There can be rubbing, things like that. There is something called oil whirl, the fact that they support on oil actually creates this instability that I was talking about, and nonlinear instabilities. Cracks in rotating shafts are quite common. They are very, very tiny invisible cracks, but they are spinning, and you cannot stop the machine, you do not know where it is, and before you know it, it explodes, and that is again a nonlinear phenomenon. Okay. And finally, a lot of the explosions in rotating machinery in oil drilling, a lot of them, every now and then you hear about a fire and explosion, but half of them are related to just the rotor dynamics of rotating shafts. Okay. Usually there is a little bit of extra vibration, something rubs against each other. It's usually a flammable situation. The thing catches fire, and then before you know it, especially if you have oil or gas, it just explodes, right. So, a lot of almost like explosions due to cracks are about I did a survey about 10 years ago, because I was doing some work on that. There were about 120 explosions in 10 years in America, in North America alone, right, which we do not necessarily hear about, and about with about 6 or 7 people dying, right. So, these are huge issues, and many of them you do not hear about because they are out there somewhere. They are not in crowded areas. Okay. So, they are an issue. This is I have a disclaimer here. I really do not know if this is caused due to why it was caused. I just said wind turbine failures, and I was like 100 hits immediately, and this is a wind turbine. Wind turbine is a rotating shaft, same thing, right. It is the same thing. And here, of course, the problem gets big, because these are hundreds of feet in diameter. I mean, these are huge structures basically, right. And this has become an issue. So, now they are worried about how do we prevent this from happening. Okay. So, that is the job of diagnostics, all right. So, the diagnostics is basically, can we spot a problem before it turns catastrophic, and why is it so difficult to do this? Like, what is the big deal? Because we find problems with so many other things, right. So, why is this a problem? Well, the first is that typical model is nonlinear, and like I was saying, nonlinear models are not amenable to easy solutions. They are difficult to deal with. Okay. So, that is the first problem. Nonlinear models are difficult to deal with. Secondly, usually most of these systems we are talking about, they are not small, they are they are large models. The larger the model, the more complex, the more difficult they are to analyze. Okay. The more difficult to predict. So, that is second problem. The third problem actually is a really critical problem, that is there is a fuzzy understanding of many mechanisms. That means I really do not know what the physics is. A lot of this physics, underlying physics is guesswork. Okay, today, right, and we have not really, we made some progress, but not enough. So, we still do not know why this happens, right, and we just throw something in there. Remember approximations, we come up with some model. Well, that is not quite accurate, right, that is the problem. And then because in all dynamic systems, this is another key thing, the response could be counterintuitive, means the way the system behaves is not that intuitive. So, to give you a simple example, if you take a a chair, and if you sit on the chair, when it is not a dynamic system, you are just sitting on it, it will that if you sit on it, and if I happen to be heavier than I sit on it, it is going to deflect a little bit more, it is going to go down a little bit more. It is like obvious, right? It is obvious growing up, that if you put too big a thing on it, it is going to break. So, that is a static system. A dynamic system does not behave like that. Many dynamic systems, it may make sense to actually make this system smaller, make it larger, depending on what happens, right. So, a lot of this response even in a linear dynamic system is very counterintuitive. It is not, you have to kind of develop the intuition after analyzing it, and that is a problem because you really do not know. For example, one common issue with a crack, if you could take a crack in a rotating shaft, the moment you get a crack, your vibration level goes down. It does not go up, it goes down. So, if you are if you are driving in a car and your vibration kind of goes up, you say something is wrong with my shocks. That's more common, right? But that's not always true. So, in situations like this, because of a nonlinear effect, the response vibe goes down, and you say, oh, everything is hunky dory, no problem. Well, before you know it, then suddenly it goes up, and then it explodes, right? So, you really, and there are interesting physical reasons why that happens. So, it's counterintuitive. That's what makes it difficult, right? And then what's normal, what is abnormal in machinery, like you don't know. There's always, nothing is going to be ideal. It's always going to have some little defect here and there, right? So what's normal and what's abnormal? When should I stop the machine? So you cannot just keep stopping these machines left and right. You don't throw away a drill because there's a little bit of vibration because it gets hot, because maybe it's supposed to get hot, maybe it's supposed to be a little bit of vibration, and maybe change a little bit, but doesn't mean I should throw it away. You really do not know, right. So, the critical issue is, when is the right time to intervene? When should I say, now is the time I need to bring this down and do some kind of maintenance, replace something, right. That is a very difficult problem. Okay. So that is something that has been occupying my interest, right, and as well as, so we have been using both physics and data-based models to do that, right. All right. So I want to talk about, I am sorry, I am talking about unmanned systems and robotics. Okay. So, before I go into this, I just want to say that there is some confusion between unmanned systems and robots, right. Of course, robotics has been an area for at least 40-50 years now, with factory robotics, where you have if you ever seen a picture of a automobile assembly line, a robot goes in and puts in a screw, or paints it or something like that. So, that is often called factory robotics, right. So, that has been there for a while, but the recent interest in robotics, what they call robotics, is being more mobile robotics, which means robots that move. Okay. So, there is this sort of a fundamental difference between these two. The second thing that is confusing is so called unmanned systems. For example, the drones that are being deployed in primarily in Asia, South Asia and Pakistan, Afghanistan, right. So, those are the drones. The drones are basically unmanned air vehicles, right, but that is really not a robot, because it's really more like it's more like these RC cars that you buy in Radio Shack for $25. It's really the same thing, except the remote control is thousands of miles away, right. It's happening here in Kansas or something like that, right. So unmanned systems are not necessarily robots. Robot tends to mean that it can function by itself. Okay. So, but I put them together, right. So here are some examples of current unmanned systems. I emphasize current because these exist today, right. So let me just go over them very quickly. So, for example, this is a robotic vacuum, right, which is now you can buy in Costco, right. I mean, it's not, when you can buy it in Costco, maybe in 6 packs, I don't know. Now it's now it's like it's there, it's you got it, everybody got it. So how is that? Well, it is unmanned. It kind of works by itself, but it's not very intelligent. So all it does is it comes up against something, it just avoids and walks away, and just something, right. And works very well. It learns. So I mean, I've seen that in working. This is a Sony robotic dog. They're they're Aibo or something like that. So they got all these robotic pets. I think it's really exploding in Japan apparently, right, because of old people. A lot of old people, all the young people have left for Tokyo City, and the old people left in the villages. So they're providing all these. There's a lot of development going on right now. So, these are fairly low technology things, right. This is a much higher technology. This is the Asimov walking robot by Honda. If you get a chance, just search for Asimov and watch a YouTube video on this. It's amazing, right. It walks up steps. They've had it play soccer, play the piano, does all these things. And so this brings a lot of newer technology into it. This is a Google driverless car, which was really the Stanford car that Google bought with their money, right. So I wouldn't say Google developed this, but it's a Prius that's been modified. The driverless cars, the prediction is that by 2020, the first driverless car will appear on the road. By 2030, they say 80% of cars on the road will be driverless, okay, autonomous, relatively autonomous, right. Which to me is amazing pace of progress, right. That's according to AAA, the prediction according to AAA, not some science people, right. This is the Predator drone. That's the drone that's been remotely controlled. This is an unmanned tank, and of course, once you have advanced technology, it's mostly funded by defense. So the defense sees a lot of applications, right. So this is the tank, like this, of course, again the DoD. This is a jet ski that's been modified to. I've actually seen this in operation, and this is a quadcopter, a helicopter, basically, right. So these are all kind of unmanned systems. So what do they all have in common? So I'm going to show you this. There's a lot of detail here. So I don't want you to focus on this, right. So let me just show you kind of roughly what a robot looks like. You kind of have this sensor layer. So basically, again, a good way of thinking about robots is to think about human beings. So as human beings, what do? We kind of sense, right. We sense things. So I'm kind of seeing something. If I want to walk from here to the door, I'm using my eyes and maybe my ears too, right, kind of listening to people talking and so on, to kind of see the surroundings. Then I perceive, meaning I have a perception, which means that helps me build a model for myself and kind of where I am and what am I doing, that kind of thing, right. And then I control myself. There's a control layer, which means I kind of control my legs on where they should go, right. And there are many different levels of control, right. And then I may have a higher level of control, which says, okay, what do I want to do? I want to go to the door, right. There's a higher level, kind of a thing, right. Why do I want to go to the door? Because I want to get out of this room and go down the steps, right. So I have this higher level, what's often called mission level control, that tells me what, like my lower level limbs, what to do. And many times the limbs work by themselves. We don't even consciously tell them, right. If I want to walk, I just walk. I'm not saying, okay, now put the right foot forward and put left foot forward, which is what I tend to tell robots, right. It's kind of just doing by itself, because there is often what's called a learned control. The limbs already have learnt, what to do, right. So there is all these different levels of control that we try to put into robots, okay. That's, because again, the humanity is a good model for it, because we know that we are good robotic systems, right. Okay. So the sensor layers will be different for robots from us. They also need maybe a camera, they need a GPS and all these things, as you might imagine, right. So that's the typical robotic architecture, right. Now in this architecture, there's one aspect, and I talked about mission, and like I want to kind of do a certain thing. So there is something called autonomy in this concept, right. So again, I'll just give you a general sense of what autonomy is. So autonomy is where systems are able to perform diverse missions in disparate environments with minimal to no human action, right. So if I could get a robot to do what I just said, just go from here to there and decide that it wants to go outside, it has a map of it or builds a map as it goes along and actually does it, that's an autonomous system. Now if you think about human beings, if you think about a 2-year-old child, actually a 2-year-old child would have trouble doing that, right. Maybe a 4-year-old would be able to say, yeah, if to go outside the building, I need to go outside this door first and actually figure that out, right. I don't know, I'm just guessing here, 2-year-old, 3-year-old, I don't know, right. Some could be precautious and figure this out at 2 years old, right. I don't know, right. You're saying it kind of depends. So autonomy is not a question of yes and no. It's really more of a level of autonomy. Okay. So according to the Department of Defense, again, which is into this, there are 10 levels of autonomy, and most of the current robotics technology is something like 2 or 3. So we have a long way to go before a system can get so autonomous that it can kind of do all the whole thing, like a human being. Okay. It turns out that this worm, by the way, has been researched a lot. This is called C. elegans, and it has 302 neurons. It's 1 millimeter long. It's been probably the most dissected worm in the world. Okay, poor thing. In fact, I think there was a micro, I think it's called a nano knife actually, but it's more like a micro. that would section this in fractions of a micron, right, and then you analyze the neurons in this, and they actually built I forget what it's called, but the full map of the neuronal connections, right, and it's the only one that they built it for. So they can understand that what it does, when it does something, how the neural impulses flow in the system. Okay. In order to understand how is that it's autonomous, it is autonomous. It can find its food, it can find, I think it's hermaphroditic, but it can find its mate, right, and then it can it performs all the basic bodily functions, it reproduces, it finds, I mean it tries to run away when you try to subject it to your knife, right. So it kind of does it does all whatever it needs to do, and we are not anywhere close to that, right, so so that's an interesting system. So one of the questions that I have proposed, and we actually got a small grant to do this, is how do biological systems develop a virtual picture of themselves. So does it know, and so this is a big interesting question, right, of consciousness. Does it know what it's doing, and does it know why it's doing it, right. So this is a big research topic in biology, right. So I read a few books on consciousness, which is pretty interesting, right. I didn't understand much of it, but I'm saying, do they know what they're doing? So if this worm doesn't know what it's doing, that's not easy to figure out, right. Right, that's a big question, but the question is, does it know that it should be doing this, but it's doing this, so there's some problem with it. So if we can have a robot do this, then we have a situation where the robot can correct itself, right, or kind of figure out what it should do to correct itself, right. So that's the sense of autonomy that we can put into the system, right. And the idea that I have is use some of those models that we are talking about to build it, right. So we just started to do this work. I'm going to skip this because that's basically the concept of that. Okay, so I'm going to just go over a couple of these projects we have done. I apologize that it's very sketchy, but if you have questions, I can answer them. Okay, so this was something that one of my students did, developed a biped robot. So we were looking at it saying, and this has nothing to do with autonomy. We just wanted to figure out how to build a robot that walks, and people have done this, of course, but we were looking at we were interested in optimizing this. We want to make this better and better. So basically, we built two legs that walk, and this is sort of a simulation of a torso, right. And my student, actually I should say my student did this. He theorized that if you use your torso in some optimal fashion, you will walk with much less energy. And the way he found this out was he was observing videotapes, he played them over and over again, of runners, and saying that the torso was being used in an optimal fashion. So we wrote a model for this, and of course I wasn't happy with the model, in a computer model, so we wanted to experiment it, and we actually found that something like 90% efficiency by doing this, using the torso in an effective manner when you're walking, right. So the untold story is that this thing doesn't have good lateral support. So if you, it's like a people with ACL injury. So if you don't support it, it'll just fall sideways. So but it doesn't look like that. It looks like it's walking. So this was another project I worked on. So it's an interesting project. So I thought I'll share this with you on an unmanned sailboat. So this is a project. A company came to us and it built this unmanned sailboat. These are solar arrays. There are solar arrays here and here. So it's powered by solar. It's powered by wind. So these can pivot, like sails. And so the idea was that this would go out in the ocean and just survive forever, and do whatever you wanted to do. And this particular boat has spent 6 months in the Atlantic Ocean with storms and hurricanes and whatnot, and survived, right. So I don't know how we did this, but it's very, very robust. It finally failed because of a bearing failure here, it turned out. Okay, yeah.
What's the scale of that boat?
Yeah, I'm sorry. This is 16 feet. Yeah. So it's it's pretty tall as well, right. Yeah. So it's about 16 feet. So there's a lot of real estate to put whatever you want on it, whatever controller. So we helped make it somewhat autonomous, right. He needed to know where does it go, can you point it to a certain direction, GPS location, and say go there. So trying to figure this out. And Dr. Singh also, Polly Singh in electrical, worked with optimizing the solar system. So all right. So here's another project we did, and people here who are part of this. This is a competition called RoboBoat competition. It's a national autonomous boat competition. Can you build a boat that will kind of go through a channel like this and do certain tasks? Okay, it's gonna like they come up with silly tasks, but basically it amounts to things like picking out an object, pointing at something without any remote control. So, it is not like a drone, it has got to do it by itself, right. You let it go, it has got to do it by itself, just using a camera. So, this was our boat, and this is sort of the path. It is supposed to kind of go around here and do certain things. Okay. So, we did fairly well in this. So, I have to say that we did not really, we were fudging a lot of autonomy in this, right. But fortunately, they did not know, so we ended up winning second place. Actually, I should say that other people were also fudging it, so we happen to be better fudgers, I think. What do you say, Joe? I think so. So, actually Joe is there, Nick here, right. So, we actually ended up winning a second place, and this is a national competition with, you can say international, because a couple of companies, a couple of other countries sent teams to it. So what happened was, this year we got invited to, well, we didn't invite, they put out a call for proposals, and we put in a competition called Robotics. So, Robotics involves a boat like this, and this boat's about 16 feet, 14 feet. This is 16 feet, but we had to work with a 14-foot boat, and they selected 3 teams from US, and we were one of those selected, and there are 15 teams from 3 each from US, Singapore, Japan, Korea, and this should have been Taiwan, sorry. So, we are one of them in team with FAU, Florida Atlantic University, Embry-Riddle, and MIT, and we are getting up for this competition in November 2014. So, the object, this is the actual satellite map of that area. So, this is Singapore, and the idea is that again it's gonna, boat's gonna kind of take off from here, and this is about order of 200 meters or so. Okay, so it's gonna take off from here, do certain things, avoid obstacles that you don't know where they are to begin with. So, the boat has to kind of avoid. So, it's like this driverless car, except that the driverless car is a little more difficult because you are doing it on the road, right. In some ways it is more difficult because on the road, you could have anything, you could have a deer come across there, right, and the road could curve. But here it in some sense is a little easier, the competition is a little easier, but in some sense it is more difficult because the disturbances are quite significant, that is the waves and the currents will throw it off quite a bit. Okay. But again the idea is to kind of avoid obstacles, get to a certain point, do a certain thing, dock itself automatically, listen to look at flashing lights and get a message from that and actually send a message, do all of this in some autonomous fashion, no contact whatsoever, right. So, it is a competition, we do not know how we are going to do, but this is in November, right. So, and we have had a lot of support, external support for people, because it is a big budget project. Okay. So, my last topic here completely different, but there I hope you will see some commonalities. Okay. It is on biomedical diagnostics. So, I got involved with this. It sounds strange, but a couple of reasons. One is a personal reason. I was always interested in this, especially pediatric issues, because of something with my son. And then it turned out that, but I wouldn't just do anything. It turned out that I wouldn't be able to do anything, just arbitrary. It turned out that a lot of the stuff I was doing with machinery diagnostics was very applicable to this biomedical diagnostics. I did not realize this, that there is so much of commonality. It is almost like we can take this algorithm, change it a little bit and put it on the other one, right. It is that common. So I kind of got into this, and the more I get into this, the more I am drawn by it. So I am going to start with why do you want to do this. So I am going to say something bold, hoping that nobody here represents a doctor, medical doctor. The only good thing I can say is, by the way, a lot of these things, the doctors I work with, by the way, this project is I'm working with Children's Hospital of Philadelphia, they're all doctors, and they agree with this. They agree with this. In fact, they go out actually and they say they're even stronger than me in saying these things. So this is what I think. The problem in modern medicine is the human body is complicated, probably the most complicated system on earth, almost definitely. Okay. Everyone is similar, but they are different. We are all human beings. So just talk about human beings, and then we come up with some data, and then they say, oh, this is white male between 150 200 pounds. It kind of applies. If you are black female, it won't apply. So we are similar, but then there are all these differences that seem to guide, really make a huge difference, right. So we want to say, okay, if you eat this, you do this, will you die? Well, kind of depends. Right, and I just discovered recently that South Asian Indians, South Indians, so Indians from southern part of India are the highest risk, have the highest risk for cardiac events, right. Thin people like me actually have the highest risk, still have a high risk. So, and it's like, why? Nobody knows. Is it what I eat? Is it what I inherit? You know, nobody knows, right. So, there is a lot of these similarities, but there are differences, right. And then I say, alas, we cannot do controlled experiments, right. I think they did, you know, a few years ago. As we know, there are some famous experiments from the 1920s and 1940s in Europe especially. You know, we don't do those things. We don't say, both of you have this disease, we will give one of you medicine, other one will withhold the medicine, and then we will see what happens. We are not supposed to do that. So, we cannot, so this is something we can do with machinery, right. So, you know, there is a problem with that, right. So, meaning in the amount of information we can get. And I am interested more in children, and children are even more varied and complex. Children are growing every day. You know, we are working with neonates. Neonates, their body changes like 10-20% from day to day. So, you got some data from yesterday, well, it is no longer valid today. The body is different, right. It is amazing, and it is amazing how much changes. So, diagnostic, same issue I had earlier, is a condition normal, abnormal. With human beings, it is even more so. You know, maybe my cholesterol is 250, but maybe I am just fine, right. And maybe it's, you know, one of my colleagues' cholesterol was 110 total cholesterol, and he had a heart attack. It's like, oh, high cholesterol, high. No, not really. We don't really know, right. So, is it normal? Well, maybe it's normal, maybe it's not normal. If abnormal, how do you know how bad is it? What can be done? Prognosis can be spot problems. Okay, so looking at the time here. So how do we deal with the human body? One is the black data based approach, right. There is fever, give Tylenol. Okay, went away. Didn't go away, now give ibuprofen. Didn't go away, do something else, right. So, it is very, very data based approach. We kind of did this last time, so maybe it worked this time. Okay. Second, which is just taking off, right, just medicine is just the beginning, saying we kind of understand. Oh, this is your picture. Okay, so you know, physics, chemistry, biology and genetics, right, at local and small level. So, they are saying, you know, maybe genetically, you know, people are inclined to something, right. This is showing near a cell basically. So, can we use the model, right, and there is some of that is happening at the development of drugs, for example, right. We can understand biochemically what is going on, right. So, the question is, can we do better than this, because clearly it is not very good. I mean, we are, you know, so many things we really do not know. So, I have you know, running out of time, so I am going to kind of skip some of these things. Okay. So, I am just saying, look, we want to make a decision, and what we could potentially do is use intelligent, what is called intelligent patient monitoring. So, we have the data in a clinical environment. Can we use a model, a computer program, whatever we develop, mathematical model, to somehow help the clinician, right, not bypass the clinician. We cannot bypass the clinician, because the clinician still knows best what to do, a doctor still knows what best to do, right. But can we help them, can we give them some additional information, right, that is kind of what we are doing. So, there are two problems we looked at. Okay. One is called PVL, and I will skip the expansion, but it is basically a brain injury, okay, that happens after heart surgery. And it turns out that it happens you know, in a lot of premature infants, usually with congenital defects, like 30% of children with congenital defects have this problem, and usually specific heart defects. Okay. And what does it, you know, what happens with this brain injury? Brain injuries are pretty hard to predict, you know, maybe because the brain is again a very adaptive organ. So, sometimes they just have a little bit of a problem. In fact, most babies who have had heart surgery have trouble with balance, like 95%, right, have problem with balance. It's probably, you know, related to brain injury, right. No, they cannot, simple thing, you say, oh, can you do this? No, I cannot. I mean, I am saying 10-year-old cannot do that, right. So, there are problems with motors, and of course, serious problems can be epilepsy and so on, and of course, they could die, right. So, it is not treated right now. It is one of those issues that is not treated, there is no treatment. Okay. They can just, what they would like to do is prevent it. Okay. And skip this. Okay. So, you can do, for example, a model for this problem, and you know, you can recognize, those of you electrical here recognize there is an electrical engineering model, right. This is not very good, it is a start. You can actually model things like this, right. You can also of course use data, right. So, with data, what do? You know, you develop things, you collect things like age, you know, male or female, this is the diagnosis, you can measure arterial pressures, heart rate. There are a lot of things you can measure, okay. As as they are doing surgery, after surgery they can measure these things. You can also measure cerebral blood flow, for example, using an infrared device. You can kind of point a gun at it basically. Chemical concentrations and things like that, okay. So a lot of things can be done. And then what you can do is, again, I do not want to overwhelm you with this, but for example, you can look at things like, how is the heart rate varying over a 2-hour period, and you can do kind of other kinds of statistical analysis on this and say, is this important to predict, all right. So we are looking at that and saying, maybe it has a role to play in prediction. We do not know the mechanism, by the way, nobody knows the mechanism as yet, okay. And you can come up with decision trees like this. Again, I don't want to show all the details here, but you can say if some quantity is this, then go down this path, and if this quantity is greater than this, then you are not going to have, you are going to have PBL, or you may not have PBL. It is healthy or it has this disease, right. So you can kind of give this date. This is, by the way, what a doctor does. Doctor always has a decision tree. Stick out your tongue. Okay, tongue is yellow. All right, now let's see if your heart, your lungs are clear. He goes through this decision tree. This is no problem. Just just stay off the Philly cheesesteak, you'll be okay, right? Or you have this problem. Let's give you this and you'll be okay, right? Or this is a problem. Let's send you on to a specialist, right? So he goes through the decision tree. So we kind of what we are doing is instead of the clinician kind of putting it from his head, we are using a computer algorithm using the data to actually develop this decision tree. But the decision tree doesn't do it by itself, right? So. And typical measures are things like sensitivity, there is something called positive predictive value and so on, right. A typical thing that you predict in medicine is there a true positive, true negative, false positive, false negative, right, which means I am predicting that this is happening, that is really true, I am predicting it is happening, it is really not true. And anybody who has ever had a what is called a PSA, prostate screening, knows that, for example, there are a lot of false positives. It means you are saying there is an issue. It's quite high, right? It's I think 50% or something like that. You are saying that there is prostate cancer, but there isn't, right? So that has a negative aspect to it. So that's not good either, because then you're going to go through lots of intrusive testing after that, and that could actually kill you as well, right? So you kind of want as many true positives and as many true negatives as possible, right? Okay. So one other last problem that we looked at is CPR. So CPR, of course, I think you're all familiar with CPR. Is basically you do this chest compression and you follow it with artificial respiration. And as I found out recently, when they do this at a certain pace, and that pace is done to the beat of staying alive. Staying alive, no. Okay, it's done, which is very appropriate, right? It's very appropriate. But that's how they train them. That's how they train the residents, how they train the nurses, right? It's approximately, is it 100 per minute, something like that, right? So they have this, sort of approximate thing that they come up with, right? But the question is that right? It turns out that very small percentage of CPR is actually effective, very small. It's like 15% or so. Right? It's very, very low percentage. So CPR guidelines are based on something that was established in 1960s. And people haven't looked at this, which is amazing to me, right? And moreover, pediatric cases, they have no idea what's the best way of doing this, right? So we've been looking at this, right? So we are saying, how do you predict, or rather, how do you, optimize this procedure in order to get a better outcome? And how do you do this on human beings? Well, we're not doing it on human beings. So this is being done on pigs at Children's Hospital, right? And they're kind of giving us data, and we are working with. I think my student Ali is actually working with the pigs. I'm not. I'm a vegetarian. I stay away from them. The data is clean for me. So, okay. So let me skip this. So we're trying to optimize this. Okay. So
they're performing CPR on pigs.
Yes. Yeah. So I kind of feel for the residents and all these people who are research assistants. Mm-hmm. The doctors are not doing this. I don't think the research assistants are doing CPR on pigs. And and they induce several heart issues in it, right? Essentially, simulate a heart attack, and then they do the and there are two reasons they do that. Two kinds of things that lead to, that you do CPR on, and so they do them.
The mental image of giving CPR.
Yes. How many pigs do they have, Ali? More than 100. There you go. So more than 100 pigs, and Ali has been working with the CPR lab, with the pig lab. Excuse me. It's called the pig lab. So I mean, pigs. I think, as you know, probably many of you know, they're kind of closest to human beings in terms of organs and so on. So they think that we can maybe use that data to predict. But right now, we're just modeling the pigs. In fact, we're looking at the physical model of exactly what it looks like when you do the CPR, and we found some new things that people haven't discovered, and we think we can optimize it just based on the physics model, and then correlate with this data, and then try it out. So we want to go back to Children's Hospital and say, do this and see if this gives you a better outcome. So here's my summary on the medicine stuff. Medicine, in my opinion, is in its infancy. Really, because as a scientific discipline, it's good as a database discipline, but human body is very complicated. Children is even harder. And my feeling is that you need both modeling, computational intelligence, like we've been talking about, also expert opinions and hunches. Doctors' hunches are very good, especially old doctors. Older doctors are very good. At a certain point, I think it falls off. But until they reach a certain point, older doctors, I don't trust, to be honest with you, very young doctors, because ultimately it's experience that teaches them what's the best thing. And so there is something called experiential learning that I think that's very important, that we want to encapsulate in our analysis. Actually, that's what we are trying to do. So, and ultimately you want an individual approach. Okay, so here's my concluding thought for the talk. Okay, so dynamic systems are pervasive. I hope I convinced you that dynamic systems are everywhere. Okay, the math and science, which I didn't present here, they are surprisingly common. Okay, if you write down a mathematical model, sometimes you cannot tell which system you are modeling. They're pretty much the same thing. Okay, and ultimately the richness of the behavior that you see in all of this, the uncertainty, all of that comes from nonlinearity. Okay, it's the nonlinear dynamics that's at the heart. And the problems are such that are fascinating, but also they're unsolvable in the near future. A lot of the problems are really, you can almost tell that they're unsolvable. I mean, they're that far out, right? So they're very, very complex problems. So, which is what gives us, it's nice. At least it will see me through my retirement. That's what I'm saying. What I mean by that near future. And finally, I want to thank Gina for putting this together, and for an awesome poster, like I said. I mean, so, and of course, I don't do anything. It's all my students, and I've had postdocs over the years, and a lot of collaborators that I've had here, other universities, at Children's Hospital, and so on and so forth, at the Navy Yard. They do, a lot of the figures here, a lot of the slides here came from them. So I thank them. You cannot do anything without funding. So, I've had a lot of funding with all these institutions that supported all this research, and of course, thanks to you for listening to me and not obviously falling asleep, let's say. So, I think I've finished almost on time. So, thank you very much. I'm happy to answer any questions.